I never did.
No, yeah. I was like, I'll get around to it. But I just never did. This is a good way to like memorize.
Yeah, and really loving is so good. You have like no idea. I'm like, how do you not know how to do this?
Yeah. I really was like, mine was not easy to remember at all. So it's like,
Mine has a good pattern.
yeah, mine has a good pattern and mine does not have a pattern at all. Honestly, I have a lot of like other questions about like random stuff. I was wanting to figure out what the best way is for
Good morning, Jake. I think we're all logging on this morning early on because yesterday there was a requirement campus-wide that we get certain kinds of passwords. Some of us are already consistent with those, some of us are not. We want to make sure that we're all on board. We will need to be in SPSS today. Good morning, Hannah. We're logging into SPSS. Yesterday was a day for IT to implement a new password requirement, so we'll see how we do. Hi, Gary. How are you? Good. I'm doing okay, thanks. Okay, well, we've got 8:30, so why don't we get started? Good morning, Psych Stats.
Good morning.
Welcome to the last week before Thanksgiving break. Who's ready for Thanksgiving break? Yeah, we're getting there. We're almost there. And this week, I think we have lots of interesting things, but nothing new beyond the typical TED Ed. So it's a nice way to wrap up this particular week. And I wanted to thank you for your responses last week to Ashley Brown. She was in here sharing some of her research and sharing some of her ideas about graduate school. So thank you for your participation in that. Just to remind you that last week we were getting into these more complicated statistical analyses. We were talking about Anova and Anova, and we had a couple of journal club sessions on those topics. And today we typically would have a journal club, but because Ashley came in on Friday, that threw our schedule off just a little bit. So I think I would like to do maybe one journal club this week on Thursday. I think we'll probably set it up for that. We'll have a journal club session on another one of the favorite articles that students have reported through the years. It's called The Do-Re-Mi's of Personality, and it gives us some experience with factor analysis, which we're going to be talking about for Wednesday. So for Wednesday, there will be a TED Ed on factor analysis. It's already ready to go. We can have you finish that off on Tuesday night. We'll talk about that on Wednesday. On Thursday, we'll have our journal club session on factor analysis with the Do-Re-Mi's of personality. On Friday, we'll start signal detection theory, which will be a little bit redundant, but not entirely redundant for those of you who are in my S&P class. Okay? And then when we come back after the break, we'll do just a little bit more on signal detection theory, and then we'll have a few non-parametric tests to go from there. So that's what we're going for the next few sessions. What I wanted to do today was get us back on to SPSS, because it's been a few sessions since we've been on, and we will have one more hands-on quiz, and we want to make sure that people are okay with all of that. So what I thought I would do is start us off first with, I think, maybe the simplest of the relatively advanced techniques, which is called ANCOVA. We talked about this a while ago, but I just wanted to make sure that we knew how to run an ANCOVA. We've mentioned it, but we want to make sure that people are comfortable with this. So will you navigate with me in SPSS out to the area of our S drive that contains our practice sets. And we have an example that I think I developed in the PowerPoint on this that says ANCOVA, and it says ANCOVA Viagra. Okay, it's a very simple data set, and it has just 3 variables in there. So ANCOVA Viagra is what we're going to open up. And we'll run a simple ANCOVA, but before we'll do that, we'll even run a simpler ANOVA, and then we'll show the value of adding a covariate. Okay. That's what the C stands for in ANCOVA, and also in MANCOVA. By show of hands, how many people are there? Okay, and some of us still have it coming up. So what's really interesting, I'll give us just a little bit of background while we're waiting for the computers to warm up and for SPSS to come along the way. What's really interesting, I think, about covariates is that typically the case is that we would use these covariates to remove these nuisance variables, these variables that might be maybe masking an effect. It might be the case that we have an effect that's statistically significant, but because there's some covariate adding a lot of noise to our data set, adding a lot of variability, we actually can't find the effect of interest. So we want to pull that thing out of there. We also mentioned that there were different criteria for establishing causation, and ANCOVAs can help us along that way. Just to get us really warmed up, because it's been a little while, can we remind ourselves of the 3 conditions that are necessary for drawing a causal inference? Anybody want to help us out with those? Thanks, Victoria.
There's a correlation, there's a time order relationship between cause and effect, and then you ruled out any other possibilities.
Okay, right. So there's the correlation, and that always confuses intro to psych students because we spend the entire semester telling them that correlation does not imply causation. It's a necessary condition, but not a sufficient condition. We need to have a time order relationship where causes precede effects, and then we have to somehow control for at least plausible alternative explanations, and ANCOVA can help us with that. Okay? All right. So let's take a look now at this data set. How many people now have it up? Is that working? Okay, very good. So we have 3 variables here. We have a dosage variable, and the dosage variable is going to be our independent variable. We might be interested in understanding whether a particular drug works. In this case, it looks like we've got Viagra, and we have different values here. We have a placebo condition, we have a low dose of Viagra, and a high dose of Viagra. So we have these 3 different groups. People have been randomly assigned to those. We're measuring one sex drive, which you might call their libido. That's going to be our dependent variable. Okay? And then we also might want to know what the sex drive is of the partner, because that can certainly play a role in one's sexual activity. So we might want to control for that, because that might be actually more potent than the Viagra itself is. So why don't we do a simple ANOVA here, and we'll do it first by looking at the relationship between the dose and the libido, and then we'll control for this 3rd variable, and that is the partner's libido. So we'll take a look at the data set, if you'll join me now by clicking over here. Okay? And it looks like we have a total of 30 cases, and just eyeballing this, it looks like we've got the first 10 people, or thereabouts, 9 or so in the placebo group, then we have a low dose group, and we have a high dose group. Okay? And we're getting some kind of libido score for each of those people, and then we also have some indication of the partner's libido shown over there, the partner's sexual activity level. Okay? So why don't we see if we can run a simple ANOVA using a univariate analysis. Okay? And this is now between subjects. We haven't done this one in a little while. So how do we get the analysis going? Let's all yell it out. Analyze, okay? And then what's our next favorite click after that when we're comparing groups or conditions to each other? General linear model, and we come to this fork in the road, and you might remember that we could do multivariate, and we might do that later on this week. And we have only univariate, we have one dependent variable. We're not using repeated measures here in this particular case, so we'll stay with the univariate case. Okay? Click on univariate, and I'll just point that there so you know where to click, and I'll let you click into that. Okay? All right. And I was in here earlier, as I mentioned, our dependent variable is going to be libido. So if you would slide that over, please, we'll make libido the dependent variable. And we'll do just a simple Anova the first time around. And we'll make the dose of Viagra, those three different levels, our fixed factor. We will not put in a covariate just yet. And if you'll join me by clicking on options, and as we typically do, we want to get means for everything here. And we like to get descriptives. We like to get estimates of effect size. And what would that look like, by the way, the estimates of effect size in our SPSS output? What's that called in our F tables? People are not remembering what that's called in our F tables. Okay, so that's the partial eta squared, okay, is what that is. And then we have observed power, and we'll have a homogeneity test, and we'll have some conversation about those today. Okay, so that's what we have going on there. And if you're ready, you can click on that, and we'll go to the output. Okay, here's our univariate analysis. And we'll see how many people got that. We've got a univariate analysis there. Okay, so we have one dependent variable. We have dose of Viagra as our between subjects factor. There are the three levels. Okay, we have some descriptive statistics shown here. Levine's test, and we'll be talking about that as well as Mauchly's test. But somebody can just remind us how to interpret that. Somebody give us a little reminder how to interpret this particular value of the Levine's test. Okay, thanks.
So the Levine's test is not significant, so you retain the null hypothesis, but
Yeah.
the assumption is not working.
Okay, right. Very good. Right. So we're looking for the equality of variances, and we've done this many times. We make this gesture. We talk about how fat the error bars are. So we're going to have error bars for each of our three groups. And we're hoping that they're at least roughly equal to each other, so that we could, and the reason for that, one more time, is so that we can say that a standard deviation for one of those groups is approximately equal to a standard deviation for another one of those groups. So we can say that this mean is 1.5 standard deviations away from this mean, and we can also say that this mean is 1.5 standard deviations away from that. If they're very, very different from each other, then they wouldn't be equally spaced in standard deviation space. Okay? So that's all looking pretty good. So we can stay with that. Okay? And we can now drop down to the test of between subject effects. And remember that this is a little confusing because we have so much output here. We're really interested in the dose effect. And here's our degrees of freedom. Here's our mean square. Here's our F value and our sig value. Significant or non-significant? That P value there? Non-significant, right? It's greater than 0.05, so we're recalling from our long weekend here that the sig value is the observed P value. We want it to be less than 0.05 for us to reject the null hypothesis. So looking at this, we might draw the conclusion that, in fact, there's a non-significant relationship between the dose of Viagra and the libido. Okay? So that's what we would have. And we could also take a peek if we wanted to at the power, the probability of finding a significant effect, if in fact one was there. And we can look at the proportion of variance explained, and it's something like 15% of the variance is being explained here. Okay, so not a lot of the variance is explained, and we have a non-significant relationship here, and we just do the regular Anova. Okay? Who's all right with that? Okay, very rudimentary kind of things. You would have done that even in Psych 200. Okay, the new twist that we got into once we came to these more advanced, we're going to run the exact same analysis now, but we're going to slide in a covariate. So can we do the same procedure one more time? You'll join me by going into Analysis, General Linear Model. We'll stay on the univariate side, and we come up with exactly what we had a moment ago, but we had taken a measure of the partner's libido, which could affect our participant's libido, and we'll make that a covariate. And all we have to do is slide that in. Okay? So I'll give you a moment to jot down what you'd like to jot down about that. So it's really just an Anova plus a covariate, and that turns the whole thing into an ANCOVA. Okay? And that's the idea there. And of course, you could have multiple covariates, right? But we'll just take the case here of the one covariate, and this is basically your partner's behavior, how your partner's behavior might be affecting your libido. And we're going to try to control for that, and then see, after having removed that source of variability, do we get any change in the effectiveness of our Viagra manipulation? Who's okay with all of that conceptually? Okay. All right, when you're ready to spin it, we'll click on OK. We'll go down to univariate analysis. Okay. And we get mostly the same kinds of things here, although we do get this. It turns out that we have a Levine's test violation. Okay. So we need to be careful about whether we want to use this F. Okay, so that's an interesting change that happened. Once we took that particular variable into account, now we have a difference in our variances, but we'll leave that complication aside just for the purpose of conversation. Now we come down to our test of between subjects effects, and I'll highlight that here. Okay. As usual, we want to go to these central variables. We're really interested in the effective dosage, which I'm here. And now we have what seems to be a larger f value, and we have a sig value that's gone from the non-significant level. It was, I think, 0.1 and change last time around. Okay, and now it's 0.01. Okay, and our partial eta squared has gone up. Okay, so we're finding more of the variance in this particular analysis by partialing out the variability that was associated with the partner. And we can even see that, and that actually turned out to be a significant effect all by itself. But by partialing this one out, we now can see that we have a significant effect of Viagra. So if you were a psychologist who was hired by some kind of pharmaceutical firm, you might want to use this kind of procedure to control for covariates that you might have measured. Who's following all that? Is that working for us? Yeah. Okay. Questions on any of that? And SPSS makes it simple for us, right? That we slide in a covariate or a family of covariates. Okay. Okay. So I just wanted to get us back in, and I think we'll be in SPSS throughout the day, just peeking in to try to make some sense out of today's TED Ed. So this was an interesting TED Ed because it connects in a way to the MANOVAs that we were talking about last week when we were doing the chimpanzee music therapy. We were talking about these different kinds of MANOVAs, and MANOVAs, of course, are a multivariate statistic, and there's a multivariate interpretation and a univariate interpretation of ANOVAs, and they have interesting assumptions underneath them, and they have interesting activity in their degrees of freedom. So we'll have some conversation about all of that inside of our TED Ed. So what I'll do today is I'll project some of our TED Ed questions, and we'll see if people would like to respond to these. These are the ones that you did for this morning. Okay? And our first question is up here. Identify the names of the statistical tests that are used to evaluate the equal variance assumption and sphericity assumption, respectively, in between and within subjects univariate. So we kind of just did that, but let's yell out the between subjects case for equal variance. That test is called Levine. We just did it a moment ago. Okay? And then for sphericity, Mauchly's, okay? And they're kind of similar, they're kind of different. Some people will think of Mauchly's as, interestingly enough, an analysis of correlations, but you don't have to think about it that way. So anyway, let's build our knowledge about this. We had to go to a wiki site and read about what sphericity is, right? That's the name of that assumption. Just like we have an equal variance assumption in the world of between subjects analyses, in the world of within subjects analyses, we have the sphericity assumption. Can somebody help us out with a 2 or 3 sentence description? And you're welcome to use your own TED Ed responses if you like. So what is the sphericity thing? This is question 2. Okay, thanks, Anna.
I said that sphericity is when the variances of the differences between all possible pairs of groups are equal.
Yeah, okay. So in some way, it's kind of like a variance assumption. There are other interpretations of that, just briefly. And it's almost as if you're saying that you have comparable correlations across all the different levels of the variable. But we'll stay with the differences interpretation for today. And I do want to say just a little bit about that, that I think will be more information than you've had before about this. So now, let's say we have an ANOVA, and it's a within subjects ANOVA, and let's say that we have 3 or more levels, or maybe, more than 2 levels, right, in our ANOVA. We're going to be looking at the difference scores across all possible pairwise comparisons, and then we're going to ask about the variance on those different scores, okay? So what I'd like to do is just draw a couple of diagrams to put that into a pictorial context. So let's say that you have condition 1, okay? And you have condition 2, okay? And you have a bunch of scores here, pairs of scores. I'm measuring each of you on these 2 different conditions. And the one example that I frequently use in Intro to Psych is, let's say we went down at the Mitchell Center, and we had been hired as sports psychologists to test out Spalding baseballs. And Spalding is thinking about implementing differently colored baseballs, maybe fluorescent green, fluorescent red, and blue, and so forth. They want to see what is the hitability of those differently colored baseballs, okay? So we'll start out with just 2 of the colors. We'll say one is red, and we'll say 1 is green, that's condition 1 and condition 2. And I can administer this kind of a test in a between subjects manner. I can give everybody in this row red baseballs. And we're throwing pitches at you that are red baseballs. We're seeing how hittable those are. I had this other randomly assigned group to hitting the green baseballs. I could have made a between group comparison, or instead, I can randomly have the machine throw to you either red or green baseballs. Okay, and we can look at the hitability of those two. Who's following us so far? Okay? Simple within subjects design, not particularly interesting. Okay? Now, one of the problems that we have often in statistics is we do want to be able to draw statistical inferences that are based on an assumption of independence. Who remembers that we've previously talked about the independence assumption? It's been a long time, but there is an independence assumption that underlies t-tests, it underlies Anovas and so forth, and that is that the scores have to be independent one from the next. A challenge that arises in any within-subject analysis is that maybe the scores are really not independent, and let me tell you why. It might be the case that if it were true that I were throwing you red baseballs and you green baseballs, it really is true that Melanie is a different person than Vanessa, okay? Melanie's scores are independent of Vanessa's scores, okay? So if we did this as a between subjects analysis, condition 1 with Melanie would have really no particular relationship to condition 2 for Vanessa, right? Those are independent of each other. But let's just say that Vanessa is a real hotshot hitter, okay? Well, every once in a while you're going to get a hotshot hitter in that group. Every once in a while you'll get a hotshot hitter in this group. Those are still independent of each other. But the problem is this. If Vanessa's a hotshot hitter, she's probably a hotshot hitter if she's receiving red baseballs, but also if she's receiving green baseballs. So the idea is these scores are not exactly independent of each other. She's going to be a good hitter here, and she's going to be a really good hitter here. Okay? Who's following that? Is that working? So her scores are not necessarily independent. And then let's say I'm a really, really bad hitter. Okay? Well, I'm going to be bad here, and I'm going to be bad here. Okay? So we still, in statistics, always like to have independent events, but once we get into a repeated measure scenario, we have a violation potentially of independence. Are people following that? Okay? So how do we get around it? Okay? And this is getting back to sphericity. I'm getting there. Okay? And so how do we get around this problem of Vanessa being really... So this is what we do. Even if we have just a simple t-test, that's a repeated measures t-test, it has just these two levels. One of the ways of getting around the problem that we have of Vanessa being a spectacular hitter is this. We can take Vanessa's difference scores. We're going to do her C1 score. That's what she's doing, her percentage of red baseballs hit versus the percentage of green baseballs hit, and we'll get a different score over here. Okay? And so we get some different score that I'll call, D1, here's D2, here's D3. These are the differences for the different, for the various participants. And we just go so on down the line. So far, so good? Is that working for us? We're getting a sequence of different scores. Okay? And if it is the case that the null hypothesis were true, and red and green really are not different from each other, then can you tell me what the difference scores should average out to? If the null hypothesis is true, and red baseballs are about as hittable as green baseballs, then the difference score should be what on average? 0, okay? Very critically, right? There's about a 0 difference. So I'll draw another item over here. And what we're really going to be tracking, even in a simple within subjects case, is difference scores. Okay? So I'll put diff score over here. And the null hypothesis would say that there's no difference between those two conditions. Here are the difference scores. Okay? Here's 0. And you might imagine that it wouldn't be perhaps exactly 0, but it would be statistically indistinguishable from 0. If we were to take a list of these difference scores, okay, and plot them, and then say, are we different from 0 or not? Well, the null hypothesis is calling for something like that. Does that look good for us? Is that okay? But maybe green is way more hittable than red is, just as a hypothetical. Then the different scores are going to be situated well away from this. Okay? But what's neat about this is now all we have is one score. Okay? And that one score is coming from Vanessa. And then all we have is one other score, and that's coming from Melanie and so forth. So we've gotten away from the independence violation by taking the different scores. And we're now going to have a mean and some standard deviation associated with that. And we can compare that to 0, and we get either a significant or a non-significant departure from 0. That's basically what a simple within-subject t-test is telling us. Who's okay with that so far? We've gotten around the independence problem by taking a different score, okay? Now, because we're doing ANOVAs, and in a minute we'll be doing MANOVAs, but for right now, let's say we want to go up to ANOVA. This is no longer just a t-test. We have red, green, and all of a sudden we get the emergence of a blue baseball. And we want to test everybody in the room on the blue baseballs as well. So here's our third condition. And we can do something like this now. We're still going to start differencing because we're always interested in difference scores and repeated measures of times. But now we're going to have one difference for red versus green. We're going to have another difference for green versus blue, and we'll have another difference for red versus blue. So we're going to have 3 pairs of different scores. And every one of those will be its own list. Right? We'll have a list of A1 versus A2, A1 versus A3, A2 versus A3, and so forth. We're going to have lists there. And we want to make sure that those variances are comparable to each other. Just like we would had this been a between subject case. We want to make sure that the variances are the same. And sphericity then is basically testing the variances of those different scores. How wide is this? And we might call this one the red-green comparison. Maybe red and green are not different from each other. Maybe blue and green are not different from each other. Okay? But maybe it turns out that we get this huge difference, just hypothetically, between red and blue. Okay? But so we're getting very different means, but those variances on these different scores are about the same as each other. Okay? And to the extent that those are about the same as each other, we're going to get a non-significant Mauchly. Okay? Who's all right with all of that? So it's almost like we've got the same kind of an idea, but these are now different scores rather than just raw scores. Okay? That's what Mauchly is doing for us. Okay. Okay, so here we can go to how sphericity is measured. We've kind of already gone over that. Okay, interpreting Mauchly's test. Okay, and we know that we're going to be looking for the 0.05, just like we typically do. If we're lower than that, we have a sphericity violation, which means some of these different scores have very different variances than do some of the other different scores. That's what's going on here. Who's with us? Is that working for it? Yeah, that's working pretty well. Okay. Okay. Violations of the sphericity assumption, and we've got a couple of different explanations there. Let's talk about how we deal with the violations of the sphericity assumption. Okay, I wonder if you might dial down to question 7 on your TEDx, and we'll see if you can remind yourselves of how you responded to this. And there's something that we have there called the Epsilon values. Anybody want to help us out with that? Okay, thanks.
The Epsilon values basically say to what degree the sphericity assumption is violated.
Okay, yeah, they give us that, right? And maybe what we'll do now is we'll call up, we'll run a ANOVA that contains a within subjects component. We'll see if we have a sphericity violation or to what extent. We'll take a look at the epsilon values, and we'll see just how strongly those are making corrections and some other ideas for correcting sphericity violations. Okay, so I'd like to look at a couple of examples on this, and why don't we do this? If you'll join me by going out to the S drive inside of SPSS, and can we open up a file that is called mixed 3x3 visual search data. Okay, and maybe I can point here also to where this is. If you go out to our 370 resources, practice sets, it's a standalone file called mixed 3x3 visual search data. And I'm taking this right from my S&P research class. How many people have that? Able to find it? Anybody not find the file? Okay, I'll just set this up a little bit conceptually so you know what was going on. Some of my students in S&P were interested in the idea of visual search, and if you were one of the participants in this study, you'd be at one of these terminals. It was actually run in this room, and your target is a green circle, and the green circle is embedded in a bunch of distractors, and there are either 4, 16, or 64 distractors, and the question is, does the reaction time go up as a function of the number of distractors that you have? Okay, so they're measuring reaction times here, and they had people do either nothing before they tried to do this visual search task. Others of them played different kinds of video games, and the question was, would the video games improve your visual search performance, indicated by having a lower reaction time? Okay? All right, so why don't we see if we can go ahead and run this thing. Let's go first to the variable view. Okay, how many people have variable view up for this data set? Okay, so we have different participants. We have 3 different groups that we'll show you in, I can put them out on the values right over here. Okay, we had a control group. We had 2 different kinds of video games that they played before they did this visual search. One was called the I Spy video game. One was a helicopter-related video game. And then they're trying to find these green circle targets amidst either a small set size, that would be probably 4 distractors, or a medium set size, 16 distractors, or a large set size of 64 distractors. Okay? And if you look over here with me, you can see the data. Okay? And these are the different groups for the various participants. And the numbers that you see floating around here are reaction times. Okay? So they're doing a reaction time analysis. Okay? In this 3x3 design, the groups are between subject factors, and everybody's getting either 4, 16, or 64 distractors. Okay? All right. Can we do a 3x3 ANOVA on this? This will be a mixed ANOVA. So you tell me what to click on. Let's all yell it out. Analyze. Okay. General linear model. Okay, now there is a within subject component. One is within and one is between. So which one do we click on? Repeated measures, right? So just inside of SPSS, repeated measures dominates. If there's any one factor in your ANOVA that is repeated measures, you always go this route. Okay? So we'll go like this, and we'll put in a factor. I'm going to clean that up. We'll say that set size, or just number of distractors, or set size, is our within subject variable. And there were 3 levels of that, small, medium, and large. Those corresponded to having 4 distractors on the screen, 16 distractors on the screen, or 64 distractors on the screen. So 3 different levels of that variable, which they code as small, medium, and large. Okay? And we can go ahead and define that. Okay? And yours will look like this. I was in here earlier, making sure everything worked here. So here is small, medium, and large. If you highlight those and you slide those over as your within subject variable, okay? And then our between subject variable is going to be group, and that again is whether you're being primed by this kind of video game, that kind of video game, or no video game at all. And we're measuring your reaction time. How long does it take you to find that green target amidst all of these distractors? We can plop on, as we always do, the options, and we can slide those over. And we like to get descriptive statistics, estimates of effect size. Again, that would be partial eta squared, the proportion of variance explained. We'll have the observed power, okay, the likelihood of finding an effect, the homogeneity tests, and we have to click on that whenever we have a between subjects component. In this particular case, we do have a between subjects component. We'll say continue. And if you're ready, I'm ready. And we'll look at the output. Okay. And we've got a general linear model output there. You might need to dial down that. How many people did get output? Anybody not get it? Okay, we're all doing fairly well there. We can take a quick peek at a few things, and we're trying to still get back to our TED Ed question on sphericity and what do we do with these epsilon values and so forth. But just to set the stage, here are the within subject levels. We have only the one factor that has these 3 levels. Here's the between subjects factor. It has 3 levels also, so this is a 3x3 mixed design. Okay. Here are some descriptive statistics. Okay. Let's drop down to, we'll probably come back to multivariate tests. We'll take a look at the sphericity bit. Okay. And you tell me what we're going to do with our sphericity assumption. Do we retain or reject our sphericity assumption here? Reject, okay, hopefully that's clear to everybody because the sig value, which is our observed p-value here, is less than 0.05. So if they're looking at all different scores floating around here, some of the differences are not, I should say some of the variances here on the different scores are really quite different from each other, okay, according to that. So then Gabby had a nice response to the epsilon values. You can see that we have different kinds of adjustments that you can make, and SPSS makes these for you. If you have a sphericity violation, you can say, well, yes, I have a violation, but I've taken that into consideration, and I'm going to use the wisdom that we get from the Greenhouse-Geiser adjustment or the Hoyne-Felt adjustment or the lower bound adjustment. Typically, in our class, we would use the Greenhouse-Geiser, but that's arbitrary. You can have your own rules about which one. We'll just take a look at the Greenhouse-Geiser. Notice that it's a 0.75 that we have going there for our epsilon value. Okay? So now if we drop down one more box, looking at the effective set size. So this would be a domain effective set size. We'll think of this as factor A. This is our within subject variable. We started out with 2 degrees of freedom here and 104 in the error term. Remember, mean square between over mean square within. So we have 2 and 104 degrees of freedom there. And we had a really nice effect. We had an F of 179, okay? And that's going to generate a ridiculously small sig value that actually isn't 0, but it's listed here as 0 because we only have 3 digits of precision. Okay? is explaining something like 77% of the variance, and you've got a really good chance of finding that. All right, but we have a sphericity violation, okay? So can somebody, maybe if I can impose on Gabby, can you tell us, Gabby, how we take that epsilon value on the next row for greenhouse geyser, how that works, if you recall?
If it's like way lower than 0, it's worse. So you want to get closer to, I'm sorry, 1.
Okay.
You want to be close to 1. So if you're going 0 and then 1, it's worse.
Yeah, okay, right. So if there were no sphericity violation, all these would be essentially at 1, right, okay? We have a greenhouse geyser epsilon value that's a 0.75. That becomes our scaling factor. And the way that we impose a penalty on the researchers for having violated the sphericity assumption is we say, okay, you can still run your Anova, but you probably have this chance of an inflated F value. So we have to control for that, and we'll control for that by essentially taxing your degrees of freedom, which we said a moment ago were 2 and 104. We're going to tax it at the tax rate shown here in the epsilon value, 0.75. So we're going to take the 0.75, and we're going to multiply 0.75 by 2, and we'll get the modified degrees of freedom for greenhouse geyser. And they're rounding up there, but you can see that would have been 1.5. People seeing where that number came from? And the same thing, we'll impose a 0.75 tax on the 104, and that would work out to a reduction in the degrees of freedom for 70, that goes down now to 77.973. People see where that number came from, and the logic that goes on there. You might remember that when we do something like fdist inside of Excel, you get prompted for the two different kinds of degrees of freedom. Okay, and the more degrees of freedom that you have, then the easier it typically is to find an effect. You can get smaller and smaller F values and still have statistical significance. So you started out with 2 and 104. Now they're imposing a tax on that. And there are different tax rates. Okay? There's the greenhouse geyser tax rate, and that is shown with the 0.75 value. There's the Hohenfeld tax rate of 0.797. And then there's this lower bound. Like how low could you absolutely go? And that's a very, very conservative reduction. That basically cuts your degrees of freedom in half. Okay, and I think the lower bound is always at 0.5, if I recall. So we're going to take 2, multiply by 0.5, we get to 1. We'll take the 104, multiply by 0.5, we get to 52. So you cut your degrees of freedom in half. It turns out that we had such a monster F value here that it didn't really matter. Right? I mean, even after the most conservative of corrections, we still have a significant F. But what you might do is, if you're writing this up APA style, you might say that we did run a mixed Anova. It was a 3 by 3, and we controlled for sphericity by making, for example, the lower bound adjustment. Or we made the greenhouse geyser adjustment, and you would report those degrees of freedom. Typically, degrees of freedom would not be fractional, but they do become fractional once you start scaling them up by these, if you'll bear with my analogy, the tax rates that are the epsilon values. Okay? So that's a nice way of playing it fair. But all of that happened because we had to assume sphericity, because we made a univariate measure that said that you're going to have these different scores that might have different kinds of variances. When we think of it as univariate, it means one variable, and in this case it means one dependent variable. So it would be the hitting rate. Okay? But there's another way of conceptualizing all of this, and this is where I think it gets really interesting. What you could say is that any given within subject Anova, kind of like this, can be construed as a manova. Okay, remember that we said that we can have an idea like a good driver. Right? What is a good driver? Well, a good driver might have relatively few accidents, might have relatively few tickets. Right? They never get driving tickets. Right? There are different kinds of measures that you could have. Well, what is a good hitter? Well, a good hitter is somebody who hits red baseballs really well. And separately, a good hitter is somebody who hits green baseballs really well. And a good hitter is somebody who hits blue baseballs really well. So you can think of those as separate measures. And if they are separate measures, then you wouldn't necessarily expect them to be on the same scale. Okay? And you wouldn't have to worry about whether they're equal variances or not. Okay? Just like you can imagine that the number of tickets might be on a very different unit of analysis than with the number of accidents. It might be the case that when you're talking about what is a good student, it might be that a GPA is one measure of good student. It might be that SAT is another measure of good student. But SATs are measured on a wildly different scale than are GPAs. Right? So you have to say, well, we can't really say that those different scores are particularly meaningful. You take each one on its own merits, and you don't have to worry about the variances of these different scores. Okay? And because you don't have to worry about the variances of the different scores, you can instead go up here to the multivariate test, okay? And all of a sudden now there is no sphericity assumption. So when you run a multivariate analysis on the same data set, there is no sphericity assumption because you don't really care about different scores because it is assumed that this variable is not necessarily related to that variable. It's not necessarily related to that variable. These are entirely different, maybe even entirely different constructs. Okay, so you could have a multivariate interpretation of a simple one-way ANOVA. And if you do, there are some pros and cons associated with that. One is you get completely away from this entire idea of sphericity, right? Because you're not assuming necessarily that everything is being measured on the same scale. Right? Can anybody tell me a disadvantage associated with going with the multivariate method? That was one of the TED-Ed questions. Real clear advantage is that you get away from the sphericity. It's not a problem. You haven't violated a sphericity because you haven't assumed sphericity. Okay? Anybody want to help us out with one possible disadvantage? Okay, thanks.
Multivariate test is more sensitive as a univariate test.
Or it could be, right? So the sensitivity can be, and the sensitivities can be driven largely by the degrees of freedom that we have. Why don't we take a peek up here at the degrees of freedom for the multivariate test? And we'll compare that to what we had just a moment ago. So same data set, one data set, we ran a univariate analysis and a multivariate analysis, okay? So the degrees of freedom for the numerator, sometimes we call that the hypothesis portion of our F ratio, is 2, okay? So that seems pretty reasonable, right? We had 2 the last time. Let's go down over here, okay? If we assume sphericity, we had 2 degrees of freedom here, and the numerator 2 degrees. So far, so good. But then if we look at the sphericity assumed degrees of freedom for the univariate case, we have 104. People seeing that number? Okay. Let's compare that to the degrees of freedom that would be used in, for example, the Wilks lambda. Okay. For the error term, we're now down to 51 degrees of freedom. Okay. So Hannah is correct because we've greatly altered the degrees of freedom. There's a different computation for multivariate degrees of freedom. Okay. And it tends to be a very conservative estimate of degrees of freedom. Then and you can see that now we have to have a significant F with 251 degrees of freedom, whereas if we did make the sphericity assumption, and if it were safe, we'd get away with 204 degrees of freedom. And it's a lot easier to find a significant effect there, making it more sensitive. And that's a lot. How many people are following that? Okay, so you might just say up front that you're going to assume sphericity and you'll make one of these kinds of adjustments. You might choose to do that. You might just say, you know what, I don't want to deal with the sphericity assumption. I'll go with a multivariate analysis. Even if I've really measured just one dependent variable several times, I'll assume that I don't have sphericity and I'm willing to take the hit on the number of degrees of freedom in my error term, and away you go. Again, here, this particular set size was just such a large effect that it didn't really matter. Anyway you slice this deck, you're going to wind up with a significant F. But there are other times when the effect is more marginal, and then your choice of statistical test would either give you significance or not, depending in part on how severely you violated sphericity. Who's all right with all that? Yeah. Okay. And it's really interesting to reconceptualize a simple, one-way ANOVA, right, but it has just 3 levels, one variable, 3 levels, to be able to reconceptualize that as a multivariate analysis, where this is its own thing. This is kind of like a GPA. Right? This is something like a SAT measure. And this might be something like a conscientiousness score. Right? If we're talking about what is a good student? Well, good students are generally conscientious. They generally have favorable SAT scores. They generally have favorable GPAs. Those are all wildly different dependent variables. Right? And you wouldn't try to find different scores to be meaningful there. Right? Okay. Any questions on that? That's a lot. And SPSS doesn't unpack all that, but it gives that information to you. You wouldn't know just by looking at it. Gee, how are the multivariate tests different from these? But I think the epsilon values help us see some of the correspondences here, and then going back up top, we can relate that to the multivariate degrees of freedom. Okay? All right. Why don't we do one more? We'll just take a peek at one more example. Can we open up? We might even have it laying around. We might go right to the output for our, it was something like the quadratic test that we had. We looked at this a few different times. There's an RT ratio significant quadratic trend. We'll see if we can find that out on our orthogonal practice set. Let's go to open. I think we have it as output. Dial out to the S drive. Okay, and there's one that says orthogonal trend output. Okay, why don't we open that one up? That wasn't a good example because our multivariate test is all done. Okay, that one had other complications, so that wasn't a good example to use. I do want to see if we get, anyway, a peek at sphericity. Let's see if we get something here. Yeah, okay, that was complicated for other reasons. Let's not take a look at that one. Okay. All right, we'll just go back to this and see if anybody has any other questions. Okay, I did want to reserve a little bit of time to talk about post-hoc tests. That was the other main theme that was cooking inside of today's TED Ed. Okay? And we want to make sure people are comfortable with that. So we've basically done now TED Ed questions 1 through 9, or maybe 1 through 10. And questions 11 through 15 deal with the post-hoc issue. Okay? So let's go back to our TED Ed questions. Can somebody help us out with the problem of cumulative type 1 error? If you want to put us in the ballpark for the problem of cumulative type 1 error. This is, and you're welcome to look on your TED Ed responses. This is question number 11. Okay, thanks, Karen.
So basically, if you run a lot of tests, then you have an increased chance of running into type 1 error.
Yeah.
If you run a different tests and so
Yeah, right. Okay, so what the alpha level typically tells us at 0.05 is we have a 5% chance of finding a difference just by random factors alone. We shouldn't get excited about finding a difference if the difference arises just from chance factors. Okay, that can happen. We think about sampling heights, right? It's probably the case that the East Campus and West Campus have on average the same height, but you could take a sample from the East Campus and a sample from the West Campus, and it might be that a particular sample idiosyncratically, is smaller than average, another sample is larger than average. So just by that idiosyncrasy, you could have a significant difference. But this doesn't really tell us that the east side is taller or shorter than the west side. Okay? So if you keep on doing that, you take sample after sample of east side versus west side, eventually you'll find two samples that really do differ from each other, just by chance. So far, so good? Yep, okay. So we try to control for that by these post hoc corrections. Okay? Can somebody help us out with the Bonferroni correction? Bonferroni adjustment. Okay, thanks, Mark.
It works by multiplying the sig value by the total number of t-tests that you run.
Okay, right. So that the more times you try to take these samples and compare them, the more comparisons you run, you take a proportional scaling of that. Right? You might say, well, I'm going to run 5 t-tests on my data set to figure out where some differences might be within an ANOVA, and we'll need to adjust that 5-fold because you ran 5 of them. Okay? So if you had a p-value of, say, 0.01, you would now multiply that by 5 because you ran 5 t-tests, and now you'd be at 0.05. Arguably, you would still be statistically significant because you're at the point you just made it, but after the post-hoc correction, you're still at the 0.05 alpha level. Okay? So that's the notion there. Okay? Imagine that we have run an ANOVA and then conducted 5 t-tests post-hoc. If a particular t-test had a sig value of 0.015, would we, dial down, retain or reject the null hypothesis after Bonferroni corrections? We all yell it out. Would we retain or reject? Retain, and the reason we're going to retain is, somebody help us out with that. Thanks, Sarah.
When you multiply the sig value by 5, if you ran 5 t-tests, it ends up being 0.075, it's greater than.
Okay, right, so let's take a couple of other variations on that. Okay. Let's go down to, I think it's question 14. Imagine that we have run an ANOVA and then conducted 2 rather than 5 t-tests post-hoc. If a particular t-test value had a sig value of 0.015, would we retain or reject the null hypothesis? We're going to reject it, and for the same reason. Okay, so we're going to multiply that by 2, and that's going to get us to 0.03, which is less than 0.05. So we've corrected now for multiple comparisons, and we we've taken care of that, and we still are statistically significant. We might say that that particular analysis was robust to the Bonferroni correction. Right? We made the Bonferroni correction, and we still had statistical significance after all of that. Okay? And people are following that. Okay? Now, so there's quite a debate that goes on in research about whether these tests are really doing anything for us. Everybody recognizes that you probably do want to make some form of correction. Okay, but we also remember from, I think, our very first exam, which was a written take-home exam, we talked about the problems of hypothesis testing, and that hypothesis testing is always very vulnerable to set size and sample size, and if you get a bigger and bigger sample, you can drive your alpha level down further and further and further. Who remembers that? Is that sounding good for us? Okay. So basically your degrees of freedom are going up, so the critical value for t, or for f, or for r, or for chi-square, those values are coming down, so it gets easier and easier to find them. And so, yes, you can make a Bonferroni correction, but this isn't really the same. That doesn't really mean that your effect size has gotten bigger as measured by partial area squared. It doesn't mean that you've influenced the dV more with your IV. It's just a matter of what you're doing with this alpha level. Okay, we have just a couple of minutes left. Okay, and maybe we can open it up very broadly and see if we reflect a little bit. This is our metacognitive moment, to think about the univariate and multivariate assumptions that we have. Okay? What seems most clear or least clear to you about those, and similarly, if anything is not so clear on these post-hoc corrections and cumulative type 1 error, we can check that out too. Any questions on any of that or something? Yes, please.
Can you talk about the difference between univariate and multivariate and SPSS, and if you wanted to use univariate in the multivariate analysis, there was a question on that. I forget how it was named.
Okay, yeah, okay. So let's just take a peek at some of our SPSS output, right? And the idea is that you can have a multivariate interpretation of a univariate, okay? And so let's see if we can just say a little bit more about that. So let's go to one of the ones that was working for us. Okay, this one I think works pretty well. Okay, so this really is a univariate test. Those students who are in my Psych 341 class really did run this 3x3. They really are measuring only one thing, and they're measuring reaction time. So straight up, it looks like a univariate analysis, and in Psych 200, that's what we would have told you to do. And it was,
some of it is repeated.
so because one of the variables is repeated measures, it opens the door for not only a univariate interpretation, but also a multivariate interpretation, where each one of these three measures now can be construed as an entirely different dependent variable. It turns out that it really was RT in all three cases, but we can pretend that it isn't. And we can say this is RT in the green condition or RT in the medium set size condition and so forth. Okay, so now you could reinterpret this as a multivariate analysis. And if you were to do that, an advantage is you get around the sphericity assumption. Okay? A disadvantage is you pay a penalty in the degrees of freedom, and that could make it less sensitive. Yeah? Okay? Does that help?
Yes.
Okay, something else. Yes, please.
For question 10 on the TED, I wasn't quite sure what it was asking.
Okay, let's take a look there. And we'll take a real quick look, and we'll let you go, because I do like to end on that. But for a given univariate repeated measures data set, the distinction between univariate and multivariate statistics becomes moot, and why is that? Okay, for it can become moot if we have only two levels. Okay, if this is our only analysis, okay, then we automatically satisfy the sphericity assumption because we only have one set of difference scores. Okay, so because there's only one, these two guys go away. Okay, there's only that, so you really couldn't have a violation of variance, unequal variances. Is that okay?
Yeah.
Okay. Thanks. Maybe I should reword that question. Okay. Thanks, everybody. Look forward to seeing you on Wednesday. We have a TED Ed that will bring us to factor analysis, another advanced statistic, and then for Thursday we'll have a journal club on factor analysis, the do-re-mi's of personality. See you Wednesday.
When are you going to be around? Do you have more classes available?
I am actually,
Do you know if you can come around? I'm pretty sure it happened, I can check and let you know.
Yeah, so I probably be. Okay.
So when a picture happens that way.
Okay. I'll run by my car and I'll check, and I'll let you know if it's ETS, if it is, and you want it, you can figure out. Yeah, that works, yeah.
Thank you so much.
Yeah, no problem.
Hannah, that, the question that I put in number 10 was cut off. The reason that was so confusing is a critical piece of information is not listed there. So I should have said when there are, so why is it irrelevant when there are only two conditions? So sometimes when I put in a parenthesis, TED-Ed stops. So thank you for pointing that out. My version of the question, yours was not the same.